Hi, this is lecture 29. Of Intractable to 3. In last session, we have seen the notion of metric space, just some idea. As I have said, metric space will be covered in 3 sessions. One we have already seen, just the definition, some examples, small examples, and some ideas. And in this session, we will see something about continuity in metric spaces. As I have said in the previous session, the notion of differentiability may be not very clear how to realize the notion of differentiability to metric spaces, but continuity is just straightforward. We will see again what is the definition and all, and then in the next session we will talk about something called complete metric spaces, compact metric spaces, connected metric spaces, and all that, some special kind of metric spaces, and that's all. These 2 sessions will not be very lengthy. We will not do many details. Anyways, you will see this in the topology course. This is only to give some flavor. So this is not many details will be covered in this. Only some rough idea of what metric spaces are about. We will see in this session. So now let us recall what is a metric space. A metric space is a pair x comma d. X is some non-empty set, and d is a map from x cross x to R, satisfying certain conditions. And we have seen that R has a metric, Rn has a metric, and all that. Now we are trying to declare what does it mean to say continuous function between 2 metric spaces x comma d to y comma d. We want to say not the same d, this is dx and this is dy, just to differentiate. Dx is a metric on x, dy is a metric on y. Now we want to declare what do we mean by continuity. So a function f, a continuous function, is first of all just a set function, set map from x to y. Right? These are 2 sets. I can talk about set map. A set map satisfying certain conditions. What is the condition? See, recall in the case of continuous functions on subsets of real numbers. So a function u2 v, both are subsets of real numbers, said to be continuous if continuous at a point a belongs to u, if for any sequence xn in u that converges to a, we should have f of xn converge to f of a. Right? Both are subsets of R. So one can talk about the convergence in R. This is sequence in R in U, which is subset of R. This is also sequence in V, subset of R. So this is the definition. This is one of the definition. So what we do is we try to imitate the same definition in case of this setup. X is a metric space. So as we have said, there is a notion of convergence of a sequence in metric space. What is it? The usual same idea. A sequence an in x should be convergent to some element a belongs to x if some condition is satisfied. What is it? What was the definition for this thing? Given epsilon positive, there is a n belongs to n such that for every n greater than or equal to n, we have, I am mentioning about this setup, we have modulus of xn minus a is less than epsilon. So I have mentioned in the last session that this metric, any metric, should be seen as a generalization of this notion of taking minus and modulus. So what we do is, in case of this, we will replace this quantity by d of an comma a. So this is the notion of convergence in a metric space. The same idea, we are only replacing this modulus of an minus x by d of an comma a. We have mentioned here, even though an and a are elements of x, d of that is an element of R. So one can talk about, see, epsilon is an element of R. So one can talk about whether this element is less than epsilon or not. Both these elements are elements of R. So one can talk about this relation. So now what should be the notion of continuity in F in metric spaces? The same idea here. A function F from x to y is said to be continuous function with respect to this matrix dx and dy if, where should I already mentioned here A, for every sequence an in x that converges to A, we should have the corresponding sequence in y converging to f of A. The same idea, there is absolutely no difference. For this convergence, we are using the metric dx. For this convergence, we are using the metric dy. Previously, both of them are subsets of R. So these two metrics are actually same in the case of in this case, where both of them are subsets of real numbers. But here x and y are not, x and y need not be related. So we want to specify this is convergence with the metric dx. This convergence is with metric dy. Okay. Now in case of continuous functions, there are two ways to, maybe more than two ways to know, but we have only seen two ways. One is sequence version, one is epsilon delta version. So what is epsilon delta version for continuity in real numbers? A function f from u to v, both are subsets of R, is said to be continuous at an element A belongs to U if given epsilon positive, there is a delta positive such that whenever y belongs to U is with the property that y minus A is less than delta, we should have f of y minus f of A should be less than epsilon. Now I think some of you are already guessing what I am going to write down in case of metric spaces. See, this we do not have to change anything. Here if you are planning to write y and A as elements of the space X, then modulus R minus does not make sense. We should replace that with d dx of y comma A, right. Y and A are elements of x. So dx of this makes sense, and this is a real number, this being less than delta makes sense. We should replace this also with the appropriate metric. Fy and Fa are elements of y. So if I want to replace this and this minus, we should be writing d of Fy and Fa. There is no minus here, Fy comma Fa. So this is the notion of continuity in metric spaces using epsilon delta definition. So let me say one more time, we are starting with two metric spaces x dx and y dy. We want to say, what does it mean to say a function f is a continuous function? A function f is a continuous function if a function f is continuous at this point A belongs to not u, it is x, right. We are talking about x there, x and y. So I have to replace this with x again. A function f is continuous at A if given epsilon positive, there is a delta positive such that whenever y belongs to x is such that y and A are in a distance delta, distance between y and A is less than delta, then Fy and Fa has this property. Now an easy exercise is to check that, see I already mentioned the proof of equivalence between sequence version and epsilon delta version in case of continuous functions on real numbers, in case of functions on real numbers. So now there is no big difficulty, but still write down the proof that says epsilon delta version of continuity in metric spaces is equivalent to sequence version of continuity in metric spaces. So that's an exercise that I am leaving you to check. Now, one useful thing with metric spaces is the following. One can talk about continuity between two functions that are not subsets of R. Usually this is what we have done till now. There is a map from U to Y, we are calling it whether it is continuous or not. Now one can come out of this setup and one can talk about, for example, one can talk about any continuity of a map from R2 to R. This we have not seen this in till now, right? All we know is whenever something is subset of R and both of domain and codomain are subsets of R, we know what is continuity. Now using metric spaces, one can extend the notion of continuity to something like this, R2 and R. What is a metric in R2? I mentioned in the last session, I am saying again. So given two elements x1, y1 and x2, y2, what is the distance between them? D of this is equal to square root of x2 minus x1 plus y2 minus y1 whole square. This is the metric that we are considering. Now one can ask, what kind of functions between R2 to R can be considered as continuous functions with any of this description, epsilon delta or the sequence version. So before proceeding to anything, one obvious thing to check is, see there are some obvious maps from R2 to R. What are those? Consider the projection map. Projection 1 from R2 to R. How I am defining that? X comma y is mapping to x. Projection 2 R2 to R, x comma y is mapping to y. One obvious question is the following. Suppose we take the metric, this metric for R2 and the usual metric, the modulus metric for R. Do we know if these functions are continuous or not? I mean, when we are talking about continuity in metric spaces, we should have some examples. Much before that, some very reasonable maps should be continuous maps, otherwise it will be uninteresting. So we are checking whether these maps are continuous or not. So we will check this, I will check one of this and you check the other map. So now what we have to see is the following. Suppose let us fix as some element a comma b in R2. Now we are checking. Suppose there is a sequence xn comma yn in R2 that converge to a comma b. Then we are asking if the corresponding image fxn yn does it converge to f of a, f of a comma b. Now what does it mean to say this is convergent? Given epsilon positive, there is a n belongs to n such that the distance between these two elements is less than epsilon. D xn yn comma a comma b is less than epsilon for every n greater than or equal to n. Let me write down what is this. This is same thing as saying under root xn minus a square plus yn minus b square is less than epsilon. And this is what it means. This root is still here. Now we are trying to see whether this thing is a corresponding convergence or not. By the way, what is fxn yn? This is simply xn, right? F was first projection. So what is f of xn yn? Just xn. What about this? This is simply a. Now we are trying to see whether xn converges to a or not. For that, what we need is the following. Given epsilon positive, we should find a n belongs to n such that for every n greater than or equal to n, we should have xn minus a less than epsilon. Let us try to use this to conclude something about this. I am intentionally writing same epsilon and same n for both situations. Let us see if they are related at all. So let me copy paste this. So this I am just rewriting again. So now what we want is we want to extract just this component from this. One nice thing that is happening here is the following, that this is a positive quantity. So xn minus a square plus yn minus b square is greater than or equal to xn minus a square. This is a positive quantity, so we can simply write that down. And suppose a is less than or equal to b, do you think we have root a less than or equal to root b? What do you think? Everything is positive. A and b are positive, so that's why I can talk about root a less than or equal to root b. So after convincing yourself that this is the case, then one can simply put square root in both places. Now there is a square, there is a square root, these two will get cancelled, and this gives us what? Xn minus a. Or is it xn minus a or modulus of xn minus a? So we will simply write this just to be careful. So now what we have is this quantity is less than epsilon. So this is epsilon is greater than this, and what we have is the following: modulus of x minus a is less than epsilon. There is a less than equal to symbol. There is a less than symbol. So we will ignore this and simply write just this. So so we got this condition. Given epsilon positive, there is a n belongs to n, such that for every n greater than or equal to n, we have mod x minus a is less than epsilon. So this says what? This says the first projection is a continuous function. Similarly, you can do the same thing. Instead of taking x minus a square, you can take yn minus b square, and you will get here yn minus b. What does it say? It says this sequence yn converges to b. That means f of, not f, I cannot call it the same thing. Projection 2 of x and yn is converging to projection 2 of a comma b, that is simply b. So this is one example of continuous function. So there are many other interesting maps which you would want it to be continuous functions, and it turns, many of them turns out to be continuous functions. So that is one. Then one can talk about, say, polynomial functions. So R2 in two variables, R2 to R, I am assigning x comma y is mapping to just xy. This is one polynomial. Is it a continuous function? Let me write down this as f. So R2 to R, x comma y is going to xy. Is it continuous at say 0 comma 0? Is it, how do you check that? Suppose we have a sequence xn yn converging to 0 comma 0. Does it imply f of xn yn converges to f of 0 comma 0? We have seen just before previously that one nice thing about this metric, which metric? This metric is if xn yn converge to a comma b, then xn converges to a, yn converges to b. This is one important thing to keep in mind. We are not very sure whether it is same in every situation or not. You need to check if it is same in every situation or not. But this is an interesting observation, and we will use it. So what we have here is the following: xn yn converging to 0 comma 0 implies xn goes to 0 and yn goes to 0. Now what is f of xn yn? According to this is simply xn yn, the product of those two elements. Now what is f of 0 comma 0? 0 times 0, that is simply 0. All we are asking is the product going to converge to 0 or not? Now this is boiling down to the usual convergence of real numbers. Now there is no R2 and all, nothing. We have two sequences converging to 0. The question is the product convergence sequence converging to 0, and we know this is true. So that says this function is continuous with respect to those two metrics, the usual metric on R2 and the metric, the modulus metric on R. One can go on extending this idea, maybe put a x here or a y here. Is it a continuous function? Now what we are supposed to check is the following. Suppose x and yn goes to 0, 0. Now what is the corresponding image? Image is x and yn plus x n plus yn. Again the same thing. X and yn goes to 0, xn goes to 0, yn goes to 0, this whole thing goes to 0. So this suggests that any polynomial in two variables, this is the polynomial in two variables, this is one of the polynomials in two variables, is a continuous map. R2 to R, any polynomial is a continuous. Is it only special about R2? What about R3? Suppose we take the metric of R3. What is the metric? Again same under root x2 minus x, the corresponding three components. If I take any polynomial map, is it a continuous map? That is the question. So let us fix some element 0, 0, 0, which is where we are trying to check the continuity. And the map is the following: x, y, z is mapping to say x square y plus y square x, something like that, r plus z. Right? Again, what is the notion of convergence here? The metric that we are mentioning here is the following. It is under root between two elements, say x1, x2, x1, y1, z1, x2, y2, z2. The distance between these two elements of R3 with the metric, with the usual Euclidean metric, is the following. That is x2 minus x1 plus y2 minus y1 plus z2 minus z1 whole square. Now what? The same idea says, suppose a sequence xn, yn, zn is converging to x, y, z, then xn converges to x in R, the usual metric, yn converges to y, zn converges to z. Now again, what does it boil down to? It again boils down to the set of real numbers. There xn square y, yn will converge to x square y. So this component is done. Similarly, yn square xn converges to y square x. This is also done, and zn converges to z anyways. So it says this function is continuous with what metric? The metric that we have mentioned here, the Euclidean metric. Now, one thing that is not very clear is, suppose I change the metric, I change the metric to some other metric, would it still be continuous? That is not very clear. So in the lecture notes, I will mention about some other metrics with which an exercise for you to check is, with that metric does this function turn out to be continuous function or not. Right? One can proceed with any n, Rn to R, any polynomial map is a continuous map. Now, so before we proceed to anything else, do we know any polynomial maps between Euclidean spaces? Let us take this R4 to R. I am treating this as A, B, C, D, mapping to determinant of the matrix A, B, C, D. Right, I could have written here as R2 square, but whatever. So now we are asking whether this map is a continuous map or not. So now all we know is just that the polynomial map is a continuous map. So now let us see what is this. Determinant of ABCD is what? It is AD minus BC. So suppose we treat this as 4 variables A, B, C, D, the determinant map is just this polynomial map AD minus BC. So in that case, this map should be continuous map, because we have seen previously that polynomial maps are continuous maps. So in this case, for R2 square, R4, this map ABCD going to the determinant, it turns out to be just this polynomial map. I am assuming you know the determinant map for any Rn square, Rn square to R, A goes to determinant of A. This thing, if you know the definition, it is a polynomial map. If you don't know the definition, maybe the first thing you need to do is you need to go stop the video, go back and check the notion of determinant. That's a polynomial map. So that says this function is a continuous function. So this is the time to be slightly happy about how much we are trying to learn. We are trying to connect between the linear algebra that we have seen, the determinant, and the usual analysis. The notion of continuity we know only for subsets of real numbers, right? You might have seen the multivariable calculus continuity, but that's only just some idea. We are not very sure whether you understand completely that or not. So but here we have a precise meaning for notion of continuity using metric spaces, and we have seen that this is a continuous function. So determinant function is a continuous function, and see, now one interesting thing to do would be the following. You recall all the maps from linear algebra. There is a trace, there is what else? There are some other things. So check if all those are continuous functions or not. Trace is the continuous function. That is very trace is a very obvious polynomial map. What is trace of this ABCD? It is A plus D. So we are taking some variables and then adding them. That is all, which is very simple thing, much simpler than the determinant. If you take the 3 by 3 matrix, determinant is for me it's slightly difficult to write down what is determinant. But trace is very easy. If you take any matrix of order R n, trace is just sum of the diagonal elements A, D. So trace is a continuous function, and you can just search in your linear algebra textbook, take all the maps and check whether how many of them are continuous functions. That is an interesting exercise for you to think about. Now we will try to get a other equivalent definition of continuous functions using the so-called open subsets of metric space, subsets in metric space. So in real numbers, I might have mentioned the notion of closed subset of real numbers. There is also an open subset I might have mentioned, but I am not very sure whether I mentioned it or not. So I am saying it again. So take a subset of R. A subset of R is said to be open if for any element in that there is a neighborhood around that is totally contained in the set. So let me say U subset of R is said to be open if given A belongs to U, there is a delta positive such that y minus A minus delta and A plus delta is totally contained in U. So once we fix A, one can find a delta positive such that this whole interval of length 2 delta, delta on the left side, delta on the right side, this whole thing is contained in U. This kind of subsets are called open subsets of R. So for example, if you take say 1, 2 subset of R. Now if you take 1 belongs to this 1, 2, and suppose let us take epsilon to be say half, then the interval 1 minus half and 1 plus half is not subset of 1, 2, right? whenever you take this interval contains say 3 by 4. That 3 by 4 is element here, but 3 by 4 is not element of 1 comma 2. Similarly, you take any this exercise, check that this is not an open subset in this description. So I mentioned that for 1 by 2 it is not happening, maybe for 1 by 3 it is happening, 1 by 4 it may be happening. So check that it is not happening for any epsilon positive. Given 1 belongs to 1 comma 2, if you give me some epsilon positive, then there is element y belongs to this, that is not an element of 1 comma 2. So usual open sets are the basic open sets. The basic open set looks like something like this: a comma b, open interval, that's why it is called open, and just the name and this definition matches appropriately. So this is the notion of open subsets in R. Now what we are doing is we are trying to generalize this notion of open subsets in metric space to metric space. So now what do you think we should do? Whenever there is a element belongs to that we cannot do anything. Real number, there is no necessity to change. Whenever there is something like an interval, we have to change it correspondingly to something called open ball, some ball. We will write on what is it. So the definition: a subset U of metric space x comma dx is said to be open if given A belongs to U, there is a delta positive such that the set ball centered at A with a radius delta is totally contained in U. Right, it's already in U anyways. What is this? This is the following set: elements of X such that distance between A comma Y is less than delta. If you observe, this thing is same thing as this. Right? Let us say, I don't want to say just casually. Let us see whether that is the case or not. Take D to the usual metric, the modulus, and UV subset of R. What is this? Suppose we take some element y belongs to R. Y belongs to R with D of A comma Y is less than delta. What does it mean? This means modulus of y minus A is less than delta. This means what? Minus delta less than y minus A less than delta. Again, what does this mean? This says A minus delta less than y less than A plus delta. So whenever y is here, y is in between A minus delta and A plus delta. That is what I mentioned here. No? So the open set in case of real number is just simply copied to metric spaces in the sense I mentioned just now. So this is the notion of open subset of metric space. Given a subset, given a point A belongs to U, there should be a delta positive such that this thing is this ball. This is called ball around A with a radius delta is totally contained in U. Now what? We will try to use this notion of open subsets of metric space to say something about the continuous function. So let us recall one more time what is the notion of continuity. Let us take two metric spaces x dx and y dy. A function is said to be continuous if given continuous at some point x belongs to x, if whenever there is a sequence an in x converging to A, we should have converging to x. We should have f of an converging to f of x. This is one description. Then there is an epsilon delta description. What is it? Again, this is fixed, there is no change. Epsilon positive, there is a delta positive such that whenever y belongs to x is such that distance between y and A is less than delta, we should have distance between Fy and Fa should be less than epsilon. Now observe that this notion of open subset is something to do with some distance should be less than some number. That is something related to this. So what we'll see is the following. Let us take so let us fix x belongs to x. Let us assume this function is continuous at x. Then what we have is the following. Whenever there is epsilon positive, given epsilon positive, there is delta positive, such that whenever y has this property, f of y has this property. Then what we are saying is the following. This phrase you will also learn when you learn some topological spaces, topology and all that. So what is happening is the following. For fixed x, in the corresponding element f x belongs to y here. Given any open set V containing f x, what we have is a open set U, open subset of x containing x such that f of u is totally contained in V. This notion of continuity, these two description implies this idea. Given a function f is said to be continuous at x if for the image, not for this, for the image you take any open set containing this element fx, there is a open set u containing x such that fu is contained in V. This is the notion of continuity of metric spaces. See, if you observe here, look at the improvement from R. In R we had the notion of this minus and modulus. Then we realized to talk about continuity or convergence, we don't really need any notion of minus or mod. That's when we reach the notion of metric spaces. Metric space, there is nothing. You take two elements, there is a D which is seen as the distance between two elements. Now one more step generalization. To talk about continuity of metric spaces, we wanted just this notion of distance between two elements. Now one more improvement is one can talk about continuity between a map between two sets without this data, but we need to have a notion of what is called open set in X and also in Y. Here also we are talking about open set, right? So we need a notion of open subsets in some setup. That notion of open subsets of a set, nothing to do with metric or subset of real numbers, is what is called a topological space. So a topological space is a set X with a notion of open subsets. See, here to talk about open subsets, we need the notion of metric and all that, right? So, but the notion of open subset can be described even without a metric. That we will see maybe in the next semester or maybe further semester. That is what is called topological space. The whole point of mentioning about the metric spaces of a planetary metric space for this course is it is a first step towards learning topological spaces, topology and all that. So I am not planning to mention the proof for this. I will mention it in the lecture notes, and that is where we will stop today's session. So today what we have seen is the notion of continuity. The convergence is straightforward. Then we talked about the epsilon delta version of continuity, and these are being equivalent. Then we have seen that some nice functions which we cannot talk about, whose continuity we can talk about in general before talking about metric spaces. Now we can talk about. There are many interesting functions. Determinant is continuous function, trace is continuous function, and maybe any other thing is continuous function. Any nice thing is continuous function. Then we have seen using metric, one can talk about the notion of open subsets. Whatever open subsets are there in R, one can just copy paste the idea to talk about open subsets in metric spaces. Using metric spaces, using open subsets of metric spaces, one can give a definition for continuity of metric spaces. Using this idea, a function f is said to be continuous at X if for the image some condition is satisfied. What is it? You take any open subset of Y containing fx, then there is a open subset containing X, containing this X, such that f is totally contained in V. Now what I am saying is, using this notion of open subsets and this idea, one can talk about topological spaces and map between topological spaces, a continuous map between topological spaces. This more details you will see in the next course. I am not planning to say anything now, there is not enough time also. So that's all for today's session. In the next session, we will talk about some nice, some special metric spaces, we will kind of metric spaces. So some of them I am mentioning here. So one is complete metric space, compact, connected, and something similar. These are the only three things that we will see in the next session. And just like this session, next session will also be very short. We will not do many details. This is only to push you slightly towards the next course of topology. That's all for today's session. We'll meet in next session.